Alright, so this problem says, classify the following equation based on the information provided. If a reaction occurs, predict the products, determine the physical states, balance, and write ionic equations. And so we need to figure out what classification, because that's going to help us then figure out what products. And there are only two kinds of equations for which you have to write ionic equations, and three kinds of equations for which you have to predict products. The three kinds of equations for which you have to predict products are combustion, single replacement, and double replacement. And double replacement includes a subcategory of acid-base. This is one of those double replacement and acid-base reactions. You have to classify it in both ways. With double replacement, the front part of one compound is going to join up with the back of another. And the front part of this one then joins up with the back of this one. And so they basically switch out. Sodium's going to go with sulfate. Okay, somebody called this outsides and insides. So Na is going to go with SO4. And H is going to go with OH. And you might notice that I didn't take this subscript and transfer it over here. Subscripts only travel when they're part of a polyatomic ion. So this subscript is part of this polyatomic ion. It travels. This subscript here is not part of a polyatomic ion, so it does not travel. Okay. So before we do anything else on this, we need to know whether or not we're going to have a driving force. Because if there's no driving force, there's no point in going any further. We just cross all this out and write NR if there's no driving force. But one of the three driving forces is the formation of water, and this is water. So the three driving forces for a double replacement reaction are the formation of water like we have here, or the formation of a gas, or the formation of a solid. And this all assumes this is taking place in an aqueous environment. I didn't tell you this is aqueous. I probably should have. So this is aqueous, and this is aqueous, and this is aqueous, and this would be a liquid. Okay. So water is always going to be a liquid as a product, unless it's taking place in a combustion reaction, because in a combustion reaction you're creating a lot of heat, and when you have a lot of heat, water turns into steam. Now we need to balance the formulas, and this is already balanced. One hydrogen ion has a plus charge, one hydroxide ion has a 1 negative charge, so that's charge balanced. This is not yet balanced. Sodium has a 1 plus charge. We know that because it's in column 1 of the periodic table, and all the metals in column 1 have a 1 plus charge. Sulfate's one of the polyatomic ions you're supposed to have memorized. It has a 2 negative charge, so to charge balance this formula, I need a subscript 2 on this sodium sulfate. Now that we have the formulas balanced, we're ready to balance the equation. To balance an equation, you don't touch those subscripts. Once the formulas are balanced, you leave them alone. And to balance an equation, you always write atom inventories. So we're going to write elements in a vertical fashion here. I left a little space over here because what I want to do is to keep track of what's on the right side and the left side. So I'm going to have a vertical column here for counting. Okay? So let's see, we've got sodium and oxygen, hydrogen, and sulfur. And so we're going to create a kind of a little mini spreadsheet here. And we're going to count all of these elements on the left side and all of these elements on the right side. And so the ones on the left side go in this column, the ones on the right side go in this column. And so we're going to count 1 sodium. We have an oxygen here and 4 here, so that's 5 oxygens. We have a hydrogen here and 2 here, that's 3 hydrogens, and 1 sulfur. On the other side, we've got 2 sodiums. We've got 4 oxygens plus 1 over here, that's 5. We've got 2 hydrogens, and we've got 1 sulfur. So we've got to try to get both sides to have the same number of atoms on both sides. Otherwise, we're violating the law of conservation of matter. And so we want to only use coefficients to balance an equation. We can't change anything in the formula, so we can only put coefficients in front of each of these formulas to get everything to balance out. Since I have 2 sodiums on the right, I'm going to put a coefficient 2 here. Now, you always want to balance oxygen and hydrogen last. So we're starting with sodium. If after balancing the sodium, the sulfurs are unbalanced, then we're going to go to that next, because oxygen needs to be last and hydrogen next to last. So let's cancel out now, or cross through the 1 for the sodium and the 5 for the oxygen and the 3 for the hydrogen, because we're going to change those numbers because of this coefficient. This coefficient means I now have 2 sodiums, and I have 2 oxygens here plus the 4 over here. So I've got 2 oxygens here plus the 4 here, so I currently have 6 oxygens. Okay? Now I have 2 hydrogens here and 2 here, so I have 4 hydrogens. So now that we've got the sodiums balanced, we're going to save oxygen for last, hydrogen next to last, and we're going to go to the sulfur. The sulfur's already balanced. So the next thing I need to do then is to go to the hydrogen, because we want that to be next to last. Since I have 4 on the left and only 2 on the right, and this species contains the 2 hydrogens, I'll put a coefficient 2 in front of this to change the number of hydrogens to 4, and that also changes the number of oxygens. And the oxygens for oxygen I have 4 oxygens here on the left, or for the sulfate here, plus the 2 now. This 2 means I multiply all the atoms in this formula, so I have 2 of those, so I have 6 hydrogens now, oxygens now, so now that's balanced. Okay? So now the equation is balanced. Alright, now then, we predicted the physical states because these symbols here are the physical state symbols. We're ready now to write the ionic equations. And the only equations for which you have ionic equations are single replacement and double replacement. And since this is both double replacement and acid base, and I need to write that down here somewhere. I'm going to do that after I do the ionic equations. Since this is a double replacement reaction, we will have an ionic equation. And so for ionic equations, we're going to undo what we did when we balanced the equations to start with. We will look at the charges and break them apart. So sodium, we said, had a 1 plus charge. Hydroxide has a 1 negative charge. And they're going to split up. Any ionic compound or any acid that is also aqueous gets split up in what's called a complete ionic equation. Any ionic compound or any acid that is also aqueous gets split up in an ionic equation or in a complete ionic equation. And so this 2 outside here means I have 2 sodiums. So we're going to write 2 Na, and since we're splitting it up by ions, we're going to put the charge on there. Sodium has a 1 plus charge because sodium is in the first column of the periodic table. And this is aqueous, okay, because we started out being aqueous. In fact, we'll find out later on in a later unit that in water, these actually do break up into separate ions, and that's why we do this. Then this is a polyatomic ion, hydroxide, one of the polyatomic ions you're supposed to memorize, and that's going to also be broken up, and we have 2 of those. Okay, and it's aqueous because we started out aqueous. All right, now we've got this acid here that is aqueous, so we're going to split it up. Now, there's no coefficient out in front, but there are 2 hydrogens in this acid. And so we're going to split it up into 2 hydrogens, and they have a 1 plus charge. Hydrogens in an acid always have a 1 plus charge. And this sulfate is a polyatomic ion you're supposed to memorize. It has a 2 negative charge. And it's aqueous because the compound started out aqueous. Alright, so I need to put an arrow here, not a plus sign. Okay, so we've got 2 sodiums in this formula. Two sodium ions, to be more correct. And then we've got a sulfate ion. Now, the only things we split up are things that are ionic or aqueous, ionic or acid that are also aqueous. And this is not aqueous. Okay, it's also not ionic. It turns out to be, this is covalent. So we're going to keep that just the way we have it there. So we've got 2 of these waters. Okay, so that's our complete ionic equation. All right, when we break up everything, we've got a complete ionic equation. Now the next kind of equation, ionic equation, it says ionic equations plural, is called a net ionic equation. In a net ionic equation, we only keep those things that change from one side to the other. And so the only thing that changes in this equation is the hydroxide, the hydrogen, and the water. If we look here, this sodium ion is also a sodium ion over here. It's also aqueous on both sides. We also have two of them on both sides. So that's called a spectator ion. It doesn't change. It's not doing anything. So it's not going to be included in the net ionic equation. The hydroxide here is an ion. It has a charge. It's aqueous. Over here, it's not an ion. So this one's changing to this, and so we're going to keep that and keep that. The hydrogen ion's the same way. We have a hydrogen ion with a charge. It's aqueous over here. We have two of them. Over here, they're not ions anymore, and they're not aqueous. And so this one's changing. We're going to keep that and the water. And the sulfate is exactly the same on both sides. SO4, 2 negative charge, aqueous. SO4, 2 negative charge, aqueous. So the sulfate we don't keep. So the only things we keep are the hydroxide ion and the hydrogen ions and the water. Okay? You can write it as HOH or you can write it H2O. It doesn't really matter. I prefer HOH when I'm doing acid-base reactions because it shows how the thing came together. Okay? And so I need to classify this. I said I kind of waited at the end, even though it was one of the first things we put up here. This is a double replacement reaction, but it is also that subcategory of acid-base, and I have to classify it in both ways. Okay? So in Chemistry 1, we don't have to deal with this, okay? But when you go on to future chemistry classes, there are redox equations, and we don't do those in this particular class. In redox equations, sometimes you'll have only, say, one sulfate on the left and two on the right, or maybe two on the left, one on the right. You can only cancel the number you actually have that are the same. So let's say I have one on the right and two sulfates on the, one on the left and two on the right. I can only cancel one sulfate. See what I'm saying? Now that's not going to happen in this class, but it will happen in future chemistry classes if you go on in chemistry. So we know this is an acid-base reaction, and the simplest way to explain this is that we have a hydroxide on the back of this formula, and we have a hydrogen on the front of this one. The hydroxide on the back of this one makes this a base. The hydrogen on the front of this one makes it an acid. Okay? Now this is the simplest of all of the ways of classifying it as an acid-base reaction. These are called Arrhenius Acid and Arrhenius Base.
So like basically, if it like the reaction makes like something and H2O.
Okay.
Can't do carbon dioxide.
Correct. You could, yeah. So the question is, if I make something and water, is it always acid-base? That's not always true. It is usually true, but especially, like you said, not when we're making carbon dioxide, because that would indicate you have a combustion reaction. You can't say that in a blanket way. There are times when that can happen otherwise. You have to have if you have an acid like this acid here, and if you have a base like this Arrhenius Acid and Arrhenius Base, you are always making a salt. So that's a new definition for a salt, and you need to know it. This is how chemists define a salt. A salt is the product of an Arrhenius acid-base reaction other than water. Okay? So if we don't include the water, then that has to be the salt. Does that make sense? That is a chemist's definition of a salt. The product of an Arrhenius acid-base reaction other than water. Okay, so for this equation here, we're going to use the same requirements or the same instructions. You're going to predict the products, determine the physical states, balance, and write ionic equations. Okay, and so this is taking place in water. I've got a compound here with more than one element. Okay, and I've got I think you should know by now it's ionic. We got a polyatomic ion here, making it ionic, and we've got an element by itself. And so when we have these conditions, then this would be a single replacement reaction, but it's going to take place only if the element that's by itself is more active than the element it's like in the compound. And in terms of like here, aluminum, that's this element that's by itself, is a metal, and the part of this compound that it's like is the zinc ion, which is a metal in its original state, or when it's not bonded with anything, it'd be a metal. So aluminum, if it will displace the zinc, will have a reaction. And so in this level class, you can't use the activity series on the test. You can use, however, the standard reduction potentials list, and it's a pretty good stand-in for this. If a metal is lower on this list, it's more active than the one that's above it. Okay? So we're going to look and see if the metal that's by itself is lower and therefore more active than the one that it's like in the compound. And aluminum is located right here, and then zinc is located right here. So aluminum is below zinc, so aluminum is more active than zinc is. So this reaction will take place. Aluminum will displace zinc. Okay? So aluminum is going to kick out zinc, and it's going to join up with the sulfate. And then that's going to get zinc over here by itself. I've often talked about this as being like, this is a couple going to the dance, and this is some guy going to the dance by himself, and you know, he basically gets rid of the male date there and goes home with a girl. So that's one way to think about it. All right, now we need to, we know we have a driving force here. We know we're going to have these products. We've got to figure out all the physical states. Sulfates are mostly soluble. There is no exception for zinc. So in water, a soluble compound is going to be aqueous. Okay? All metals, when they're by themselves, except for mercury, and there's one rare one, which we won't deal with in here, are going to be solids. Okay? Sulfates, again, are mostly soluble. There's no exception for aluminum, so we'll say this is aqueous. And zinc, again, is a metal, and that's solid. We need to balance the formulas. Well, these two were already given to you, so you can assume that when we balance, it is. Zinc has a 2+ charge, and sulfate has a 2- charge, so that's charge balanced. The aluminum is by itself, so it has no charge. Actually, it's a 0 oxidation number. Aluminum, when in a compound, has a 3+ charge. Sulfate has a 2- charge. To charge balance this compound, we're going to need 2 aluminums and 3 sulfates. Okay? And so now we have the formula balanced. We've got the physical states all laid out. The next thing to do is to balance the equation. And to balance the equation, you can't change these numbers. These are now set in stone. Okay, leave them alone. Set in stone. Leave them alone. Now we're going to write a list of all the elements we have in this equation. We have zinc. We've got sulfur and oxygen and aluminum. We're going to make a kind of a little mini spreadsheet here to keep up with our count here for the atom inventory. And so we're going to count all the zincs over here. We've got 1, all the sulfurs 1, all the oxygens 4, all the aluminums Al 1. Over on the other side, we've got 1 zinc. We've got 3 sulfurs. We've got 4 times 3, or 12 oxygens, and we've got 2 aluminums. We want to balance oxygen last, so I can start with the sulfur if I wanted to. So they've got 3 over here. In order to get 3 over here on the left side, I can put a coefficient 3 in front of this species. I can't do anything with the formula. I can't put 3's here anywhere in the formula. I can only put coefficients out in front once the formula is balanced. That's going to change the number of zincs and sulfurs and oxygens. So now we have 3 zincs and 3 sulfurs and 12 oxygens. And so now that I've unbalanced the zincs here, I'm going to go over to the other side, and I'm going to put a coefficient 3 in front of the zinc, which will change the number of zincs to 3.
You already got 2.
Okay. And then I got 2 aluminums here. Go over on this side, and I'll put a 2 there, and change the number of aluminums to 2, and we've got a balanced equation now. Okay. So I haven't written down the classification. I'm going to do that in a minute. But we've balanced the equation. We balanced the formulas, then balanced the equation. We have physical states. We've got an atom inventory. Now we're ready to write ionic equations. So we first write the complete ionic equation. We break up everything that's either a salt, like this and this. These are salts, or these are ionic compounds that are also aqueous. Or you would also break up, if you had the acids that are also aqueous. So we're going to have zinc broken up. We've got 3 zincs. Zincs have a 2+ charge when they're in an ionic compound. This is aqueous, so this is going to be aqueous. So if you have an ionic compound here that's aqueous, then the separate ions down here are also going to be aqueous. And so now we have 3 sulfates. Two aluminums. And we got 2 aluminum ions over on this side because this is an ionic compound and it's aqueous. 3 plus. We've got 3 sulfates. Oop, should be SO4. And then we've got 3 zincs over here. All right, now, this is a complete ionic equation. It shows everything, all the ions that are broken up, and everything else in here. For the net ionic equation, we're only going to write the things that change, okay? So this zinc ion has a 3 plus charge and it's aqueous. That's not the same thing as a zinc solid. So this is a change. We're going to keep those 2. If you were writing, if we were balancing equations that were redox, we would give this a 0 charge because when it's not combined with anything, when it doesn't form an ion, an element that's by itself is going to have a 0 charge. Now this 3 sulfate ions, SO4, 2 negative aqueous, is exactly the same as this, SO4, 2 negative aqueous. So we're not going to include this in our net ionic equation because it didn't change. The aluminum, the solid aluminum here, did change to aluminum ions, so we're going to keep that. And that's the net ionic equation. Now we don't do these in here, but this is the basis for the way batteries work. Okay? This actually illustrates how electrons are moving around. The electrons on this aluminum left the aluminum and joined up with the zinc. And that's why we have a 3 plus aluminum here and a 0 charge on the zinc over here. So this is a redox equation, even though we don't do redox in here. Elements that are by themselves that are not part of a compound. Okay, so zinc metals are by themselves, not part of a compound. They have a 0 charge. Okay, if we have hydrogen gas, that's H2. Okay, but that's a gas. It's not part of a compound. It doesn't have an existing charge or anything. That also has a 0 charge. If we had oxygen gas, that'd be the same way. Okay, CO2 would be a 0 charge overall, although that really doesn't matter because that's a compound, but we're talking about elements here. Elements would have a 0 charge.
So there's no acid or anything like that? Y'all had the rehearsal yesterday, but you weren't here. Awesome. I know. I thought it was filled with
If my voice is still bad, I'm going to tell Linda that I can't do it.
I prefer double replacement and single displacement. Okay, we had a guest speaker the other day who called this double displacement, and it sometimes is. And we can also call this single replacement. But I just prefer double replacement and single displacement. No, I won't count off. Sure. So there are many different types of acid-base reactions. There are 3 major classifications of what acids and bases are, but we're only dealing with right now the simplest of all the acid-base reactions, okay? And so they go by the definition of what an acid is. And so for an acid at this time, it's called an Arrhenius acid. And an Arrhenius acid has hydrogens on the front of the formula, okay? Technically, they're more broad than that, because if we have an Arrhenius acid actually is anything that gives away hydrogens into an aqueous or water environment. But for us, we're going to go with really simple acids like, we could say HClO3 or H2SO4 or, let's see, H3PO4. Okay, that's our simple sort of acid we're working with right now. Okay, and so a really simple base for an Arrhenius base, an Arrhenius and base, will have hydroxide on the back. So it might be calcium hydroxide. It might be potassium hydroxide. It might be sodium hydroxide. Okay? I'm sorry, hydroxide. It is hydroxide, right? So Arrhenius acids are going to have hydrogen in the front, at least the kind we're talking about for this definition right now. And the Arrhenius bases will have hydroxide on the back. Okay? So an Arrhenius acid-base reaction is going to react this acid with this base, for example, and the hydrogen is going to join up with the hydroxide, and we're going to get water. And this calcium is going to join up in this case with a chlorate ion, and we get calcium chlorate. Okay. In this case, it's the hydrogen on the front of this sulfuric acid. It's going to join up with the hydroxide. We're going to get water. And the potassium is going to join up with the sulfate. And in this case, this is phosphoric acid. The hydrogen is going to join up with the hydroxide. And the sodium is going to join up with the phosphate. Okay? And so you're always going to get water and an ionic compound over here. Okay? This ionic compound is by definition then what a chemist would call a salt. Okay? You always get water and a salt when you have an Arrhenius acid-base reaction. Okay? And so this ionic compound, and you should know it's ionic because in this case this one contains a polyatomic ion. Well, all these contain polyatomic ions. So there's two kinds of ionic compounds you should be able to recognize. Okay? One, or ways to recognize an ionic compound would be if it contains a polyatomic ion like these do, or if you have a metal combined with a nonmetal. Okay? Either case will give you an ionic compound. But by definition, if I have an Arrhenius acid-base reaction like this, I want to produce water and a salt. So we can define a salt, or a chemist would define a salt in this fashion. A salt is the product of an Arrhenius acid-base reaction other than water. Okay? A chemist would define a salt as the product of an Arrhenius acid-base reaction other than water. Now, I haven't gone through and given physical states to any of these, but we could do that if we wanted to, because that's something else you need to do in this unit.
Are we going to put physical states in all the formulas?
In this unit you have to have physical states for everything. Okay. Now, let me just, a little word of warning. Phosphoric acid, we'll find out when we get to the acids unit, actually ought to be listed as a solid and not as an aqueous compound, but don't sweat that right now. Okay. Well, we won't do it, but when you get to redox equations later on, weak acids like this, we won't get to what weak acids are until we do the acids unit. Weak acids are listed as solids. Not right now, but just a word of warning, it's coming up. Okay, so hydroxides are insoluble. So hydroxides are insoluble. There's no exception for calcium here. And so this is going to be a solid. Hydroxides are mostly insoluble, but all group 1 metal salts are always aqueous, or always soluble, and therefore if there's water around, they'll be aqueous. This is the same category, aqueous. In an acid-base reaction, there's no heat, so all these waters are going to be liquids. Well, there's heat, but there's not significant heat. And then this would be, this compound here, this chlorate ion, always forms soluble compound, so that's aqueous. This is a group 1 metal salt, so that's aqueous. And this is a group 1 metal salt, so that's aqueous. Okay? Of course, I haven't gone through and balanced things yet either, because that should be 2 here and so forth. But this just, I'm just writing this out as a definition for acids and bases, or an acid-base reaction. Yes, so this is both double replacement and acid-base. And when you see one of these kinds of equations or reactions, you have to classify it as both of those things. Okay? For us, all the acid-base reactions we're going to be dealing with in this level of chemistry will also be acid-base. I mean, will also be double replacement. So you can have just a double replacement reaction, but if you have an acid-base reaction, you have to classify it as both acid-base and double replacement. Okay? Okay, so if we have a reaction such as this one, I have a polyatomic ion here, so that's an ionic compound. There's a hydrogen on the front of this, so that's an acid. So we're reacting an ionic compound with an acid. This is a double replacement reaction. Okay, anytime you're reacting ionic compound, two ionic compounds together, or ionic compounds and acids, you're going to have a double. You're going to assume at this point in time, anyway, that you're going to have a double replacement reaction. So in that case, then the front part of this goes with the back part of this. Some people have called this outsides and insides. Okay, the outsides go together, and we have NaNO3, and nitrate compounds are always aqueous if there's water around. Group 1 metal salts are always aqueous if there's water around, so this is aqueous. And then the hydrogen's going to join up with the carbonate, and this is where the bells and whistles should go off. When you have hydrogen joining up with carbonate, then you're forming carbonic acid. Okay? And this is carbonate has a 2 negative charge, hydrogen has a 1 plus charge, we get this. And if you look up this on the solubility rules, if you've memorized your solubility rules, that's supposed to be aqueous, but that's not really going to end up that way because this automatically, immediately starts to decompose. And so what we have is this is actually breaking up into water and CO2 gas. Okay? Yes. It'll start to bubble. All right, so really what we need is not this reaction written this way, but this reaction replacing this with these things. Okay? So what we're going to do then is write the equation in this manner. And it's actually a two-stage reaction, but what we do in here anyway is always write out what the final stage is. All right. So the original equation, double replacement, had no solids being formed, no water being formed, and no gases being formed. And so you would, if you just looked at that and didn't realize there's a second stage to the reaction, you would say that's no reaction. But in fact, there is a reaction because we're actually producing a gas. That makes sense? And so one of the three driving forces for double replacement reaction is the formation of a gas. Everybody understand that? And let's see. That's probably a good time to review. Yeah. Driving forces of chemical reactions, okay? You must know that what kind of reaction is involved. You have to predict the products for only three kinds of equations: combustion, single displacement, and double replacement. The driving force for single displacement reactions, I should say reactions, I guess. Whoop, back it up here. Reactions in an aqueous environment is when an element by itself is more active than something like that it's like in a compound. And then also metals are like metals. When we say like here, the word like there, okay? Then like refers to the fact that metals are like metals and the hydrogen in an acid. Okay? So let's and then halogens are like other halogens. All right? You need to remember that really active metals make water act like an acid. Okay? The very active metals like sodium and potassium and lithium will take the hydrogen off of an acid and make H2 gas, the way that all metals will, a lot of metals will do that with just the regular acid. Okay? That's the very active ones. Okay? So really active metals make water act like an acid. Okay? And so we're talking about double replacement now here, at least we were a moment ago. So in double replacement reactions then, the driving force for double replacement reactions, it should be, not reaction singular, but plural, in an aqueous environment is the formation of a solid, which means we're forming a precipitate, the formation of water, or the formation of a gas, which is what this example with carbonic acid was about, formation of a gas. Okay? Any questions about that? All right. So don't confuse this because we're forming water and CO2 with a combustion reaction. A combustion reaction, at least in this level class, is always going to start with a hydrocarbon and oxygen. So we're not starting with a hydrocarbon and oxygen here. Okay. A combustion equation will have a hydrocarbon, say this, all right, and oxygen, all right, and for us, these carbon chains like this that are 5 carbons or smaller, we're always going to call a gas, okay, and oxygen's always a gas, and anytime you have a hydrocarbon reacting with oxygen in this class, where we're just beginning to learn about chemistry and the basic reactions that occur, we're going to assume that we're always going to make carbon dioxide gas and steam. Okay? Those are always going to be the products. So predicting the products of a combustion reaction is the easiest one. Now I know that's water like this is, and that's CO2 like this is, but you also have to consider that we're starting with something else. We're starting with a hydrocarbon and oxygen. So this is a combustion reaction, and this one's not. This is actually a double replacement reaction that has, as part of it, a decomposition. Okay? Now, if you're given the name cyclopentane, and it doesn't just automatically in your head you can figure out what the formula is, just figure out the structure and figure out how many carbons and hydrogens. So cyclopentane just has a circle. And we've got 5 carbons, 1, 2, 3, 4, 5. Ends and bends, remember, are where we find the carbons. Okay? And so every carbon has to have 4 bonds. We're only showing single bonds. These single lines here are for single bonds. So each of these carbons have 2 bonds going to it. I need 2 more bonds. And so you terminate that with a hydrogen. Right? Remember, hydrogen is our terminator. So each of these carbons then has 2 hydrogens on it. So the formula, the simple formula, the molecular formula is just C5H10 because it has to have 2 hydrogens for every carbon. So we said that carbon chains, for us, to really simplify it down, to make it easy for right now, it's not really always true, all right? But for us, to make it simple, we're going to assume that any carbon chain of 5 carbons or less, that's going to be a gas. Any carbon chains greater than 5, up to and including 15, we'll say is a liquid. And then above 15 in the carbon chain, we'll call a solid. Okay, that's for hydrocarbons only, okay? It's different when we get functional groups on there, but for us, that's all we need to deal with right now, okay? So we're going to kind of keep it simple, 5 and 15, okay? Just like when we're doing, let's see, what was it, polarity. We said that 0.5 up to 1.5, right? Those are our 2 breakpoints. I'm trying to keep it kind of simple for you, all right? Because there's a lot of things that go into it that affect these things. That might make it not a liquid or might make it not a gas. But for us, for right now, we're trying to keep it simple because you just don't have the background information to make other kinds of judgments about physical states.
And that's just hydrocarbons?
That's just for hydrocarbons.
So does that mean, like, added up the numbers, or is that just...
Well, 5 carbons. This is going to be a gas.
And
up to 5 carbons in the chain. So we've got 5 carbons in the chain. That's going to be a gas. More than 5, so for us at least, we would say that this compound would be a liquid, because this is C6H12, so we'll call that a liquid. Now, you go to take an organic chemistry class, and don't try to tell your organic chemistry professor that that's the way you do it, because this is just kind of a, training wheels right now, okay? It's the training wheels on our little bicycles, okay? So in my honors chemistry classes, excuse me, you're not allowed to use the solubility rules or the activity series on tests. You have to memorize solubility rules. But the activity series, you can pretty much get everything you need for the activity series by using a reference that you can use on the test, and that's the standard reduction potentials list, okay? And yes, the most active metals on this list are at the bottom, and the least active at the top, and the halogens are the opposite, the most active at the top, least active at the bottom. And they're kind of mixed together on here, so you have to be able to recognize when you've got an acid, you've got a metal, and when you've got a halogen displacement, single replacement or displacement going on, okay? But yeah, you don't have to have the activity series if you got this, because 95% of the time this does just great for what you need to do, okay? Got it? So if you're looking at the activity series, all right, lithium is at the top, then rubidium, then potassium. If you go over here to this one, lithium's at the bottom, and potassium, rubidium, and so forth. Okay, pretty much in opposite order.